Today we talk about time complexity, right? First topic is the running time, right? The running time, or we can say execution time, right? Okay. Of a program is the total time it takes for a computer to execute that program from start to finish for a given input, right? Just imagine you are searching for your friend's name in your phone contacts, right? If your contacts list is small, you find it fast, right? If you have 2000 contacts, it takes longer to scroll and search, right? Think the more contacts, the more time it may take, right? That examples mean running time depends on input sizes, right? In that example, the input size is taken as the contacts, right? We measure running time in steps, right? Not seconds. This makes the analysis machine independent, right? We have three types of running time and we will deeply explain those after, right? Running time is expressed asymptotically to describe how it grows as the input size increases, right? We have two perspectives to measure the running time. The first one is the actual running time, right? In this type, we measure running time in seconds, milliseconds, and nanoseconds when you run the program on real hardware, right? The second one is the theoretical running time. In this type, we express it using big R notation, which describes how the time grows with the input size, right? Theoretical running time is another way of saying time complexity. Complexity has two types, which are time complexity and space complexity, right? What is the space complexity? Space complexity is all about how much memory the algorithm uses, right? We have 7 different types of complexities in Big O, right? Here you can see in order from best to worst, right? Don't panic. Let's learn one by one at a time, right? O1. Constant time, right? This is the easiest one. Even if your input gets bigger, your algorithm takes the same time, right? Think you look at a specific student in a class list by index, right? Examples, accessing an array element. We can represent it like this now. Accessing array, right? And checking the top item in a stack and swapping two numbers, right? In this case, if you want to find a value in an array, as soon as you see it, you can grab it, right? The next one is the linear time. We can represent it as this, right? This is the most common complexity, right? The time increases directly with input size. If the input doubles, time also doubles, right? Think you check every item in your shopping list to find milk, right? Simply remember, checking every item one by one is equal to linear time, right? If you want to search 100 in this array, you should check one by one. 10 is 10 equal to 100? No. Then move to next. 25 is not equal to 100. 30 not equal to 100, 100 equal to 100, right? That time you found it, right? This is the simply we can say, right? Next one is the logarithmic time. We can represent it as this, right? This one sounds scary, right? But it's actually simple once you see the idea, right? Okay. Logarithmic happens when you cut the problem in half each time, right? Think of it like this. You have 128 pages, right? Instead of checking every page, you fold the search, right? Like this, 128, 64, 32, 16, 8, 4, 2, 1, like this. Only 7 steps, right? That's logarithmic, right? Examples: binary search, searching in a sorted list by dividing into halves, many tree operations like BST search, right? The next one is the linear rhythmic time. We can represent it as this, right? This is a combination of linear and logarithmic work, right? Linear rhythmic means you divide logarithmic and then work on each part linear, right? Think of it like this. You cut a cake into halves, right? But you still have to eat all pieces, right? And so the work becomes this. This, right? Okay. Common examples: merge sort, quick sort, heap sort, many efficient sorting algorithm, right? The next one is the quadratic time, right? We can represent it as this, right? This happens when you have nested loops, right? Quadratic means for every element you loop through call elements again, right? It grows fast. If n is equal to 10, we can get 100 steps, right? If n equal to 100, we can get 10,000 steps, right? And think, for every student, you compare them with every other student, right? Examples: bubble sort, insertion sort, selection sort, checking all pairs in list, right? The next complexities are exponential and factorial, right? Example for exponential: subset generation, brute force on many combinations, some recursion problems, right? What are the examples for factorial? Traveling salesman brute force, all permutations of a set. These are usually avoided unless n is very small, right? And these are the worst and grow extremely fast, right? This is for factorial, this is for exponential, right? What are the factors depending on the running time of a program? We have 3 factors: algorithmic, environmental or system, and hardware, right? Let's discuss one by one, right? First one is algorithmic, right? Right. These are things related directly to the algorithm itself and the way you write it, right? What are the algorithmic factors? Input size. Bigger input usually means more time, right? Algorithm chosen. Example, bubble sort versus merge sort, right? Input characteristics, right? Example, sorted versus unsorted. And input affect quicksort, right? Implementation details. How you use data structures or code patterns. Basically, anything about how your algorithm works, what works and what it's given, right? The next one is hardware factors, right? These are about the machine running your program, right? It includes CPU speed, numbers of cores, RAM, cache, memory speed, disk speed if your algorithm involves input and output, right? Simply remember anything about the physical computer your code runs on, right? The last one is environmental factors, right? These are about the external software or conditions affecting execution, right? Included compiler optimizations, operating system scheduling, background processes, virtual machine overhead, right? Simply think anything about the software environment or system load that affects how long your code takes, right? Next, move on to complexity analysis, right? What is the complexity analysis? Complexity analysis means measuring how the running time or space of an algorithm changes as the input size increases, right? And it's independent of machine, language or compiler, right? It helps us combine different algorithms to see which one is more different, right? The next topic is what is the need for complexity analysis, right? The first reason is different computers run at different speeds, right? If you run an algorithm on a slow laptop or supercomputer, it will take different times, so we cannot trust actual running time, right? That's why we need a machine-independent way to measure efficiency, right? The second reason is running time changes with input size, right? Sorting 10 items fast, right? But 10,000 items much slower, right? So we need a way to predict how performance grows as n increases, right? The third one is to compare algorithm, right? Example, think you have two sorting algorithm, algorithm A and algorithm B, right? Which one is better? You cannot test every case, right? So, complexity analysis helps you choose the best, right? The fourth one is it tells us how much time and space an algorithm needs, right? It helps us understand resource usage, right? Fifth one, it helps measure the difficulty of solving a problem, right? It means harder problems usually need more time or memory, right? The next topic is problem solving and algorithm selection, right? First one is multiple algorithms for a problem. Let's discuss it, right? You know, a single problem can often be solved in different ways, right? For example, sorting a list can be done with bubble sort, merge sort, big sort, or even counting sort, right? Each algorithm has trade-offs in speed, memory usage, and complexity, right? The second one is choosing the best algorithm, right? When we choose an algorithm, we consider these points, right? What are those points? First one is understandability and simplicity. Let's discuss about it, right? If the algorithm will be maintained by other developers, pick one that is easy to understand, implement, and document, right? Simpler code usually has fewer bugs, right? The second one is performance, right? Let's discuss it. If execution speed and resource usage are critical, like in real-time systems or large data sets, right? And choose the most efficient algorithm in terms of time and space, right? The third one is scalability, right? Let's discuss it. It considers how the algorithm behaves as the input size grows, right? Sometimes a slightly slower algorithm for small inputs may fail badly on larger inputs, right? The fourth one is correctness, which is that the algorithm must solve the problem correctly under all expected inputs, right? The next one is robustness, right? It handles edge cases gracefully, right? The next one is reusability, right? It can parts of the algorithm be reused for similar problems, right? Next one is resource constraints, right? Available memory, CPU, or even energy, right? What are the asymptotic notations, right? Asymptotic notations are a way to describe the running time or space requirements of an algorithm as the input size becomes very large, right? Instead of worrying about exact seconds, we focus on how the algorithm grows when n
I have no intention of destroying your career or your life.
until this, right? Okay. They help us compare algorithms independent of hardware, language, or constants, right? The first one is big O notation, right? It gives the upper bound of an algorithm's running time, right? It means the algorithm will not take more than this time for large inputs, right? You can see example. This is used for worst case analysis, right? The second one is omega notation, right? We can represent it like this. It gives the lower bound of an algorithm's running time, right? It means the algorithm will take at least this much time for large inputs, right? It is used for best case analysis, right? The next one is theta notation. We can represent it like this, right? Okay. And it gives the tight bound, both lower and upper, right? It means the algorithm grows exactly like this function for large inputs, right? It uses when growth rate is well known and consistent, right? Theoretical analysis of time efficiency, right? What is it? Theoretical analysis of time efficiency is the process of estimating how fast an algorithm runs without actually implementing it, right? We focus on how the running time grows with input size, not an exact seconds, right? This is done using asymptotic notations like big O, big theta, big omega, right? Why do we do it? We can compare algorithms and choose the most efficient one, right? And we can predict performance for large inputs, and we can avoid time-consuming experiments on different machines, and we can optimize resource usage like CPU and memory, right? Steps to perform theoretical time analysis, right? This is the code snippet, right? The first, we should identify basic operations, right? These are the operations that contribute most to the running time, right? Examples, comparisons, additions, assignments, and loops, right? And etc. What are the basic operations? We have a loop and we have additions, right? Okay. These are the operations, right? We have two operations. The second step is count how many times each operation runs, right? Look at loops and recursion. We have single loop. If it is single loop, it should run n times, right? See, run n times, okay? Then, if it is nested loop, it should run n squared times, right? Okay. Therefore, runs n times, right? Then we should express running time as a function of input size, right? We can represent like it like this, right? How can we represent this? We can write it as this: T n equal to n, right? Okay. The next step is simplify using asymptotic notation, using this, right? Ignore constants and lower order terms, right? In this equation, we should ignore constants, right? Now, we should ignore the lower order terms, right? What is the lower order? I teach before. Lower order is n, therefore we should ignore it. Remaining this, right? Therefore, time complexity should be this. Okay. What are the cases? When we analyze an algorithm, its running time can vary depending on the input, right? We classify them into three main cases. What are they? First one is the worst case. The scenario where the algorithm takes the longest time to complete, right? It guarantees an upper bound on running time. It is used, bigger notation is usually based on the worst case. You can see this example, right? And the second one is the best case, right? This scenario where the algorithm takes the least time to complete, right? It shows always minimum time the algorithm can take. Big omega notation is often used for the best case. This is the example, right? The last one is average case. The expected running time for typical input, right? It gives a realistic idea of performance on random inputs, right? Often used in algorithm textbooks for probabilistic analysis, right? Why big O is not speed? Two algorithms can have the same big O, but one can be faster in practice, right? See this example. Big Boss says both are leading, but B is much faster for small n because 5 is less than 1000, right? Big O doesn't account for CPU speed, programming language, compiler optimizations, memory or cache effects, right?